Hello, everyone, and welcome to the LIUniverse. I am your host, Dr. Charles Liu, and though the winds of change may blow through the fashions of nicknaming, please call me Chuck. It is always such a pleasure to be here with you all, and especially with our co-host, as always, Allen Liu. Hey, Allen.
Hello.
Hey. Have you produced any interesting fossil fuel reactions lately?
Ooh, I mean, I use gas to cook some fun stuff.
You are a
doing a lot of
chef.
stir frying.
Okay.
That's natural gas. That's a fossil fuel. I don't know if I've done anything
That's true.
more
Because you
significant than
drive.
that.
That's right, because you drive a vehicle that runs on electricity.
Yeah, it's a
Very
plug-in
clever.
hybrid. It could potentially run on gas. I just don't drive it very far.
Excellent. Well, I ask this question in part because our guest today is an expert when it comes to using fossil fuels to work with organic materials to produce things that are, shall we say, edible? But amongst other things, also understanding how awesome black holes are in this universe. And I can't wait to hear from him. Everyone, please, let's welcome our guest, Dr. Matt Taylor. Hi, Matt.
Hi, everyone. Hi, Charles. Thanks for having me. This is really fun.
Oh, we're going to have a great time with you. Let me say a couple of things right away. First of all, you are not the other Matt Taylor, are you? You are the Matt Taylor in astronomy to which I refer. And I tell everybody this because there is another Matt Taylor who is an astronomer as well. He does planetary astronomy, and he was involved in the Rosetta mission, which landed a lander on a comet some years ago. But you are not that Matt Taylor, right? You are a different Matt Taylor.
Yes, I am the other Matt Taylor. Unfortunately, he stole the moniker before I could get on the scene, so I'll just settle for being the other one. But no,
Well,
I work on much larger scales than just the solar system.
Well, this happens all the time, right? We have a big world now, and we have different people. Like there's a different Charles Liu, for example, several, in fact. One who, for example, makes violins. I want to be that Charles Liu. That's cool. And I think there's at least one other Allen Liu floating around in the world.
I met
right?
one of them. He's a computer science guy. He was also my year in college, but not at the same place.
Oh, amazing. You are, to us, the one true Matt Taylor today.
100%.
Tell us a little bit briefly about yourself and what you're doing and where you are right now, and we'll go right into it.
Yeah, sure. So, like you said, I'm an assistant professor here at University of Calgary. Name's Dr. Matt Taylor. I'm originally from Vancouver Island, which is just on the west coast of Canada. I did my undergrad studies at the University of Victoria. Go Vikes!
Nice.
I moved down to Chile for a few years to do my PhD, where I got to visit all the amazing observatories down there.
Yeah.
Was lucky enough to get a 2.5-year postdoc in at Gemini North Observatory in Hilo, Hawaii.
Oh, wow.
Before coming back to Canada for another postdoc, and then eventually finding my position here at the University of Calgary.
Wow.
That's awesome. That's all over the place.
Yeah, you may have logged the most miles from one professional place to another of any of our colleagues. Although Sabrina Berger was also in Canada and in Australia.
That was someone we have on a different episode this season.
Right, but Calgary is further north than McGill in Montreal. So you may have the latitude record for traveling from Chile all the way to Calgary and stuff. That's impressive.
Possibly. But I think, the claim to fame really goes to my cat. My wonderful cat, Mingus, he actually went from Ontario all the way to the coast, all the way to Chile, all the way to Hawaii. He's come all the way with us. So
Amazing.
He might actually have the record for most well-traveled cat.
Mingus, like Charles Mingus?
Named after the one and the same, yeah.
Wow.
Amazing. So the jazz artist, yeah.
Yes, free jazz. Ooh, fun stuff. All right, we have so much to talk about. But first, we are going to go to today's joyfully cool cosmic thing. Now, I am very excited. This doesn't happen very often because usually the cool cosmic thing is related to, but not actually, what our guest is doing scientifically. But this cosmically cool thing is so joyous that I'm just going to go right and let Dr. Taylor, Matt, tell us about it in detail. It has to do with the discovery of a supermassive black hole in a little tiny cluster of stars. Well, maybe. Matt, talk to us about this joyfully cool cosmic thing. It was just published, so you have the floor. Tell us about this.
For sure, this is a really, really fun result that I'm happy is finally out there. So the sort of the backstory here is back about 25 years ago, so just around the turn of millennium, some folks were looking at images of the Virgo and Fornax galaxy clusters. So these are two nearby galaxy clusters with like hundreds of giant galaxies, all sort of gravitationally bound. And they were looking at these images, and they saw these objects that they knew were at the same distance as the galaxy clusters themselves. So they knew that these things weren't stars within our own galaxy. They knew that these weren't like really, really distant background galaxies. But what was funny about them is that they were very, very compact. So on the images, they were very, very small, but they were extremely bright. So they couldn't be individual stars. But they were too small. Like physically, they were just too small to be what we call dwarf galaxies. And these are sort of the lowest mass galaxies that we're aware of. So they were physically too small. But their brightness indicated that their stellar densities, so like how many stars are packed into this small volume, were comparable to what we call globular clusters. These compact star clusters that we have around the Milky Way, around all the galaxies that we know. So they were a little bit too big and way too bright to be globular clusters. They were physically too small to be dwarf galaxies, and so they termed these things the ultra compact dwarfs. And so immediately, because we're scientists, we started arguing like, what the heck are these things? Are these just big, bright, but otherwise normal globular clusters? Or more interestingly, at least in my opinion, maybe these were actually the remnants of formerly more massive galaxies. And so the idea here is that if you take a dwarf galaxy and you form what we call a nuclear star cluster, so just a really dense cluster of stars right in the core of the galaxy, and you take this nucleated galaxy and you throw it into a galaxy cluster where it then gets these gravitational harassments whenever it passes by a giant galaxy, you can strip all the stars away from it until you're left with just this compact core. And so that was one of the ideas for what these ultra compact dwarf galaxies could possibly be. And so this debate raged. It went on for well over a decade into the middle of the 2010s. And people started to say, okay, well, what would the smoking gun be? You know, what could really differentiate a large but otherwise normal globular cluster from one of these former nucleated dwarfs? And one of those smoking guns would be a central black hole. So we don't find, at least not yet, not convincingly, massive black holes in the middle of globular clusters.
Right.
But we do find supermassive black holes in pretty much every giant galaxy where we look for them. And so if we could find a supermassive black hole in the middle of one of these ultra-compact dwarfs, that would be that definitive piece of evidence that says, aha, this thing is not just a star cluster. It used to be a much, much more massive galaxy. And so people started looking, very, very hard work. And in 2014, there was a Nature paper put out by Dr. Anil Seth at University of Utah, where they had it. They found this like very, very convincing evidence of a very, very massive black hole in the middle of this ultra compact dwarf. It's called M60 UCD1. And that was it. Like it was the proof that, okay, at least some ultra compact dwarfs came from formerly more massive galaxies. And so since then, other groups have continued to look, and they racked up a whopping 5 UCDs confirmed black holes. Right? Like holy smokes, five things. And so 4 of these were in the Virgo galaxy cluster, which is a little bit more nearby. And one of them was found in the Fornax galaxy cluster.
Okay.
But then that was it. That's all we could do because technological limitations of especially ground-based telescopes just weren't able to resolve spectrally the signature of these black holes in smaller ultra-compact dwarfs.
So you knew the black holes were there, but you couldn't figure out anything about them. Is that a problem?
Well, I mean, we suspected, but that's
that
not
there were more than those 5. Yeah.
Yeah, we suspected that there was more than 5, but we just didn't have the technology to look at them. Enter, of course, the James Webb Space Telescope.
Woohoo!
Yes. With the resolution of James Webb and with the mirror size, we could start to look at lower mass and smaller UCDs to try and find more black holes.
Amazing.
And so that's where this result really comes from. So we targeted a handful more, and this is the first result coming out where in the smallest UCD ever discovered for this kind of result, the lowest mass, smallest UCD, we've discovered a roughly 2 million solar mass black hole in something that's like not that much bigger than a globular cluster. It's a really fun result.
That's fantastic.
That's amazing.
I mean, it really is amazing. The ultra compact dwarf, about how big across is it? How many light years roughly?
So in terms of light years, this would be on the order of sort of 50 million or 50 light years. Sorry.
50 light years. That's it? Wow. I mean, our Milky Way galaxy is 100,000 light years across.
Yeah,
so
absolutely.
This is tiny.
Wow.
Yet its black hole is about as massive as our supermassive black hole. Amazing.
Yeah, it's on the order of half the mass of our own galaxies. But in terms of the half-light radius, which is just kind of a parameter describing the size, it's only about 15 parsecs, and that's on the order of about 50 light years across.
Amazing. So that is so cool.
Yeah, this is like less than 1% of the size of our whole Milky Way galaxy. Less than like 0.1%.
Yeah, that is an amazing discovery.
Dang.
And you're pretty sure that there are lots of these, Matt? I mean, all around in clusters of galaxies everywhere. If we found a few already in small environments right near us, way out there must be zillions of these guys.
Oh, there must be a whole schwack of them.
Nice.
The problem, of course, is in astrophysics we're always dealing with biases.
Oh, right.
So the first UCDs looked at were naturally the biggest, brightest, and largest. Mm-hmm. And so those would be the most likely to contain these supermassive black holes. What we really need to get a handle on is how often we find them in those lower mass ones. Is it 50%, 25%? And so that's why we looked at as many as we could, as many as they would give us time to look at. To get an idea of what fraction are coming from formerly more massive galaxies or are just sort of run-of-the-mill, but just kind of atypically large globular clusters.
Wow. And just to wrap up this idea of black holes inside little tiny objects, mini galaxies, for example, or star clusters, we had on in a previous season of the LIUniverse, Dr. Vivian Baldassari, who was one of the people who was involved in finding the first intermediate mass black holes in small dwarf galaxies. Is this discovery that you've made now a completely different phenomenon from those kinds of things, or are they related in the overall construction of black holes in the universe?
I mean, the existence of intermediate mass black holes is a whole topic amongst itself.
Okay.
But the connection between intermediate mass black holes and supermassive black holes goes back to how we think black holes were seeded in the very, very earliest times in the universe. Wow. And so those connections are still relatively unexplored. But it's funny because Vivian is actually a co-author on this result.
Amazing.
Yeah, so it's funny that how astronomy works. She's a co-author on the paper, yet I've never had the pleasure of meeting her in person.
Vivian is awesome. You guys aren't that far away. She's in Washington State. So Alberta is kind of near there, right? Kind of move over a little bit and up a little bit, and there you are.
And there we are, yeah.
Yeah, and Vivian does, if I recall correctly from that episode, long distance running. So maybe you guys could
too long of a distance to run unless you're that's more of a hike at that point.
Yeah, it's a long way and over a mountain range. That
Wow.
would be a challenge.
Oh, that's super cool. But well, that's great, and I'm so happy to hear about the connections about the field, and it's really nice to be able to talk to people who are connected in so many ways other than just doing scientific research. I love that. Thanks, Matt. Cool. That is super cool, and I can't wait to hear more about some of your other discoveries that are happening with JWST and other things coming up. But right now, we're going to take a quick break, and we will come back in just a moment with our first audience question. It's a Patreon question, right?
Yep. Got some Patreon ones this time.
Oh, excellent. We'll be right back right after this break. And we're back here on the LIUniverse with our awesome guest, Dr. Matt Taylor, who is supermassive black hole expert in little tiny stellar systems and other things as well. We were talking earlier about how there are at least 2 famed, high-quality, awesome researchers named Matt Taylor in the field of astronomy. And you're the one that does the black holes, whereas the other Matt Taylor does, spacecraft landing on comets and things like that, which is super cool. But I did notice that Matt Taylor, that other Matt Taylor, has a very cool thing. He apparently is a heavy metal music fan. He does serious, awesome, that kind of stuff. Are you also a heavy metal musician, Matt?
I am not a heavy metal musician. No, unfortunately. I dabbled into listening to heavy metal a little bit in my teen years, but I'm more of a jazz 90s alternative kind of typical.
Oh, nice.
Okay. Are you a musician as well? Do you have particular expertise in musical instrument or voice or anything like that?
So I did play drums for a number of years in high school. Jazz and rock and that sort of thing. Unfortunately, it's tricky to drag around a drum set around the world. So that
is
kind of
fair.
But these days, I'm trying to get back into to playing the drums. After my time in Hawaii, I'm teaching myself the ukulele. But that's the extent of my music.
Oh, that's great. But instead, your artistic skills lie in your culinary expertise, I understand.
Yeah, that's probably what I have a little bit more experience in. I had a kind of an atypical journey to astronomy. During high school, I was one of those weird kids who had no idea what they wanted to do after they graduated high school.
I wouldn't say that's weird. I think that's normal. I think those of us who sort of knew what we were going to do already are the weird ones. But you please continue. Go on. Yeah.
Well, I'm glad to hear that. I had interest in a number of things. I always liked science, geology, meteorology, astronomy, that sort of thing. But I also really enjoyed cooking as a teenager, and so my first foray into choosing a career was actually going to a professional cooking program at what was then Malaspina College. Now it's Vancouver Island University. And then trained as a chef for about 6 years. Yeah, it was fun. But as anyone who's worked in the industry knows, it can be a bit of a rough and tumble, high stress kind of job. And,
I've heard that.
Yeah, and so eventually I was thinking more and more about science. I wasn't having as much fun cooking just because of, as you kind of rise through the ranks, it gets more stressful. And so I eventually decided that I'd move on from that and enrolled in community college because I was poor. And I did half my undergrad degree at Camosun College. Shout out to them.
Wow.
And then transferred to UVic and the rest is history.
That's
awesome.
Marvelous. Oh, I love that story.
Moving from gastronomy into astronomy.
Yeah, that's right.
Probably someone's made that joke with you before.
Believe it or not, no, I think that's actually a first. I like.
Oh wow,
really?
I'm Alan, good job. Well done. All right, we have got to get more into that later, but right now it is time for our first question from an audience member. And Alan, you were telling me that this is from a Patreon patron.
Yeah, just so our patrons on Patreon get first priority for questions. So if you want to, go to patreon.com/LIUniverse, please. We appreciate everyone who's supporting us there already, and we appreciate everyone too. So our question is coming from Taylor L. Different first name Taylor as opposed to last name Taylor. The question is it possible dark energy and the acceleration of the universe's expansion could be explained by the idea that the black hole we live in is constantly devouring matter from outside?
Whoa. Wait, which black hole do we live in? I presume this is the hypothesized black hole that we live in. I don't know. Matt, you got to take this one. This is both my...
Yeah, that's a doozy, but I love it. I mean, regarding whether or not we live in a black hole, I don't want to get myself in trouble, so I'm just going to say I think answering that is beyond my pay grade.
Fair.
But when it comes to the expansion of the universe, right, we have to remember that this happens on really, really large scales.
Mm-hmm.
So we have what we call the Hubble flow, where on scales large enough in the universe, we always see things moving away, right? So the further you look in the universe, the faster things are moving away due to the expansion.
Mm-hmm.
But on smaller scales, if you look at the local group, our local group of galaxies, the Milky Way, Andromeda, and our assortment of dwarf galaxies,
yeah,
these are all bound strongly enough by our mutual gravitation that it counteracts that expansion.
Oh,
interesting.
Okay. And so we have to remember that the expansion is really happening on those really large scales. And we talked earlier that this object that we're looking at, this UCD, is really only 15 parsecs or so, 50 light years across. And so in this case, gravity is acting on such a strong scale that the expansion of the universe probably doesn't have much to do with what's going on inside this UCD.
Mm-hmm.
So Taylor mentions the black hole accreting material, and this is actually a really important aspect of this project. Black holes, the way we see them, the way we actually collect photons from a black hole, isn't coming from the black hole itself. Right? By definition, the black hole is bound so strongly that light itself can't even escape it.
Mm-hmm.
The way we see black holes is from the accretion disk of material that's falling onto that black hole and gets heated up to enormous temperatures and provides that light.
Right.
Which means if you want to see a black hole, and I put C in inverted commas, you need material to be actively accreting onto that black hole.
Interesting. Okay.
But what we see in ultra-compact dwarfs is that we don't have any gas or dust. It's all being previously removed from these systems through mechanical energy, supernova, various effects. And so if we don't have gas and dust within these clusters, we don't have material that can actually fall onto that black hole. So we can't actually take a picture and see with photons where this black hole, and we have to infer its location, its presence, by how fast stars are moving around the black hole.
Oh, okay.
Because as you get closer to the black hole, the gravity increases, it speeds up the stars that are orbiting it. And so it's actually measuring the stellar velocities around the black hole that we're actually measuring. And so it's I'm glad that Taylor mentioned that, because it's actually a really important aspect of this proposal. It's a different technique than Vivian uses, for example, to detect black holes.
Wow. Well, Taylor, great question. I don't think we were able to give you a satisfactory yes/no answer, but nevertheless, you triggered a whole lot of interesting scientific discussion. I really thank you so much.
Thanks, Taylor. I do think that right now we don't have the information out there to be able to answer this question fully, but I'm glad you're thinking about it,
And getting pieces of the answer is how we get to the whole answer eventually. It takes a long, long time.
100%.
Wow. So, for those of you who are listening to us and not on the YouTube video, I encourage you at some point when you have the time, if you're in the car, don't do it right now, but if you are going to get a chance, go to the YouTube, because you should see where Matt is right now. All right. The background is one of the coolest backgrounds. Thank you for
Looks
modeling
like
it. For those
mission
of you,
control for the Apollo program or something.
that's right.
Like,
That's right. Because Matt is in the control room of an observatory at this moment. Please, Matt, tell us about this observatory and what you're doing here and things like that. And tell us a little bit, give us a little tour because it is cool.
Yeah, for sure. So I've recently, as part of my duties here at University of Calgary, have taken on the role of director of science for our university's observatory. So that's the Rothney Astrophysical Observatory.
Awesome.
And so we have a collection of telescopes here. The observatory itself is about 50 years old. Hence
Okay.
the antiquated
vintage
equipment.
controls. Yeah.
Hey, if it works, don't fix it. Yeah.
This is mostly for show now. So this is the original controls, these gray panels here, and it's actually just behind my shoulder here. This one screen that it's all been updated to sort of modern systems. But no, this is the control room for the ARCT, the AR Cross telescope, which is a 1.8 meter optical telescope. So this is tied for the largest optical telescope in Canada.
It's big.
It's by far the largest university telescope in Canada. And so this is a very, very cool place. And so this is where I'm actually doing the interview from.
Wow, that's great. So the telescope is like in an adjoining room or building. You're in a nice, warm, comfy place. So you don't have to be out there when it's a zillion degrees below zero.
Yeah, absolutely. Here in Calgary, we get brutally cold winters, and so this control room, it's actually just behind me here. There's some blinds in the background there, and the dome's actually just behind me there.
Oh, fantastic! Look, send us some pictures of the telescope later on. We'll put it on the show notes on the YouTube. Okay,
yeah, or
and
maybe
so people
flash
can
them
see
on the
this.
screen.
Yeah. I mean, 1.8 meters. That's 6 feet across, right? Probably 20 feet tall. It's a not a trivial instrument.
Yeah,
that's good stuff.
It's a great telescope.
Wow, I love that.
Awesome.
So, are you doing observations, not necessarily with this telescope, but other observations that have led you to another or more recent interesting discoveries that we will be hearing about soon? Can you give us a preview of some of the cool stuff you're doing at the moment?
Yeah, so I'll talk about a couple of things that I'm involved in and things that are coming out. One is an extension of this James Webb program that we have. So we didn't just look at these ultra compact dwarf galaxies. We had a collection of what we overall call compact stellar systems in our bucket of targets.
Okay.
And one was a follow-up of what we call a compact elliptical galaxy. And so these are kind of thought to be like high mass analogs of UCDs. So instead of having these compact UCDs coming from low mass galaxies, these are more like the giant galaxies that we see that get boiled down to something that's kind of like a UCD, but much larger, but similar kind of stellar densities.
Okay. So the edges have been torn off by all these interactions, but it's much larger result at the end, not just 50 light years or 15 parsecs across, but it's something else.
Exactly. Mm-hmm. Yeah. So they're like the mass of a giant galaxy, but put into the volume of a dwarf galaxy.
Wow.
Whoa. So it's just kind of a scaled up UCD kind of idea. Mm-hmm. And so this particular one was observed in the late 90s with the Hubble Space Telescope. And there's a preliminary result of a supermassive black hole. So we're talking, like 100 million solar masses in the core of this thing. And it was just an upper limit. It wasn't a really definitive result. And so we had to follow up with that since nobody had since then. And so we followed up with the James Webb Space Telescope, and sure enough, we've confirmed that in another recent paper that there's this 100 million solar mass black hole in the center of this really, really compact but more or less giant galaxy. And so
that's
this is
amazing.
A very cool result.
Well, it's great that not to interrupt too much, but that something that had lain dormant or not studied for almost 30 years, you're coming back with a new telescope and being able to make new discoveries off of this. So I think that's great. Knowing the history of what has been done before really helps us move forward in the future, right?
Oh, absolutely. It provides more information on sort of the demographics, the statistical likelihood of how black holes appear in these kind of systems.
Wow. That's great. Well, we look forward to hearing more about that later. Any do you dare tell us any super advanced ideas that we might be looking for in the coming months? The science that you're doing that might we want to hear about. I mean, because when it comes to black holes, we're always looking for the latest stuff.
But
so I don't want to make you say anything.
You don't have to
say anything that don't reveal anything beforehand. But can you give us a little hint?
Give a little sneak preview that I left out a little detail about this galaxy. It was known back in the 90s that this object actually had a double nucleus. So, normally when we look at galaxies, there's one big bright center, and that's it.
Right.
But we're finding that in a few select galaxies, they actually have two. And so that was known to be the case with this particular galaxy, where it has a big bright nucleus in the middle, and then it has a slightly fainter one that's offset by about 40 or 45 million light years. But it's slightly fainter, so it's not like the main nucleus of this galaxy.
Okay.
And so what we've actually found is that the black hole that was previously detected in the middle of this galaxy is actually associated with that nucleus that's offset from the center.
Wow.
Whoa.
And so now the challenge is to interpret why that would be. Why do we find this supermassive black hole offset from the middle of the galaxy when in most galaxies we find it right in the core? And so I'm going to leave it at that. So we're working on the interpretation. There are some really interesting implications for this off-center black hole, but we'll save the details, the juiciness of that for another time.
I love
that. Oh man, okay. We'll have to see when that gets published. We'll shout that out everywhere.
45 light years away from the center is where the black hole actually is.
That's wonky. Whoa. I love that.
Thank you for giving us that to chew on. That is so cool. I love that. All right. Do we have another question? We have another question
from another patron. This one's from Shemo. I think we've asked one of his questions a while ago.
Okay. Hey, Shemo.
Hi, Shemo. Welcome, or thanks again for giving us another question, Shemo. So Shemo's question, I've paraphrased it a little bit here because it was pretty long, but we got some good stuff from it.
Okay.
This one is, we often say gravity is weak compared to other forces, but in the right regimes, like near black holes and neutron stars or on large cosmic scales, it dominates every other interaction. So, should we stop calling gravity a weak force?
Well, that's a great question. I think you really hit the nail on the head with referencing the scale on which we're talking about. So, gravity is strong because it acts everywhere. It binds us to the ground. It binds stars in star clusters. It speeds stars up to enormous speeds if they orbit too close to the black hole. So it's natural to sort of say, well, come on, it's doing all this work. It must be a strong force. But in everyday life, you kind of prove how weak it is. Right, I'm a pretty small guy. I don't lift weights. I don't go to the gym nearly as often as I should.
You mean both?
Yeah, all I have to do is jump, and I counteract gravity. Right, like my legs alone are able to get me off the floor. Now, gravity continues to work, and so it brings me back down. But even when you look at our most powerful rockets that can launch things into space, the amount of power in those rockets is really minuscule when it comes to the entire mass and the entire energy budget of the Earth itself.
That makes sense.
And so while on a human scale, those rockets are really, really powerful, on a planetary scale, they're nothing. They're not even a drop in the ocean. So despite that, we can still counteract the entire gravity of the Earth and get things in orbit. And so I think for that reason, I think it's still fair to kind of call gravity weak, but to each their own. I'm not too much
fair.
For specific nomenclature.
Fair enough. Yeah, weak or strong, all the forces in the universe affect us significantly and profoundly.
Yeah,
and
not
gravity,
just the weak
perhaps.
force and the strong force per se. The
Right,
ones
right.
that are weaker and stronger.
Yeah, and certainly gravity, which does so much, and we see so many cool things as a result of it. So, thank you, Shema. What a great question. I appreciate it. Thank you, Matt, for that answer. I love it. The time is flying by. We have like almost no time left, but I just want to follow up a little bit on your awesome chefness. Okay, your culinary skill is so neat. What would you say in the places that you've worked professionally, right? After your culinary career, so that would be in Canada or Western Canada, more specifically, and Chile and Hawaii. What are like a couple or three of the most interesting foods that you would recommend to our listeners as we think about doing astronomy? I mean, I'm thinking of because as we're taping it now, we are close to the Harvest Moon Festival.
Yeah.
Which happens in the fall, of course, with the full moon. And the Chinese tradition is you make these moon cakes, and then you go out under the full moon and you take a bite of those moon cakes while you're looking. All right. Now, that's pretty specifically astronomical as far as culinary stuff is concerned. But do you have something that you can tell us? Like if we go down, to Chile, or if we go to Hawaii, what's some food we should really, really check out and make sure to have?
So, I mean, in Chile, if you want to get astronomical, I'm going to say empanadas.
Okay.
Not just because they're tasty, and by themselves, they don't seem astronomical. But for anyone who's been lucky enough to be at Las Campanas Observatory on a Sunday, it's Empanada Sunday, and they cannot be beat.
No
wow.
way. Really?
For Chile, if you want the astronomical tie-in, I got to go with the empanadas.
Okay.
It's what the astronomers eat. I love it.
For sure. But otherwise, I'm going to say for any listeners who haven't tried Peruvian food, because there are a lot of really good Peruvian restaurants in Chile.
Yeah, they're neighbors. Yeah.
They're neighbors, and I gotta say, don't sleep on Peruvian food, ají de gallina, or
I mean, the classic one I can think of is ceviche always, but
and ceviche, absolutely. But no, they have a number of just absolutely delicious kind of national dishes.
Wow, what was the one that you mentioned specifically? The multisyllabic one?
Ají de gallina.
Okay,
it's like a chicken stew that's stewed with ají amarillos, so these yellow, mildly spicy peppers.
Wow.
And so it's good enough that my partner and I we bought some ají amarillo seeds, and we actually grow them in Calgary. We grow them inside. We have a little hydroponic.
That's amazing.
Wow. We actually make our own ají de gallina because it's just that good.
That's awesome. That is fantastic. That is, I mean, obviously it's culinary and earthy, but it's cosmic to me. When you have food that is so good that you're willing to transport seeds for thousands of miles and grow them indoors hydroponically in another continent, that is worth having. Wow. Yeah. I love that.
Well, another
Thank
continent
you for that
if you're an English-speaking person.
That's right. Wow. Geez, there is so much more to talk about. We have to have you back, and hopefully soon. Maybe you can tell us about the stuff that comes out of that really cool idea of that supermassive
That
black hole being 45 light years offset from the center of the galaxy. Will you come back soon, please?
Absolutely.
Matt? It would be great.
I'd be happy to.
Oh, thank you so much. In the meantime, if we want to find you on the internet or social media or stuff, where can we look for you?
So I don't have too much of a social media presence, but I do have a website that I probably shamefully don't update as much as I should. But if anyone's interested in getting a bit more of an idea, then it's mataylor5128.github.io.
Okay. M.A. Taylor 5128 at github.io. And the 5128 is to distinguish yourself from the other Matt Taylor, I bet.
Yeah.
For those of you who don't know, NGC 5128 is a famous galaxy called Centaurus A, and it's in the southern hemisphere. You guys might want to check it out.
It's not just a randomly assigned set of 4 numbers. It's got some meaning to it.
No, it's got some meaning. My PhD thesis was on the globular cluster system of NGC 5128.
Oh, wow.
Oh, wow. Amazing.
Are there a lot of globular clusters around that galaxy?
There are a lot. There's several hundred. We're up to about 600 or 700, and we're still trying to confirm what the total population is. Yeah.
Wow.
Awesome.
Yeah. Around the Milky Way, we only have a couple hundred. So this is substantially more than us.
Absolutely. Yeah. It's a beast of a galaxy, but a very, very cool one.
That's awesome. I love that.
All right. Something else for us to look at. And we'll put that in the show notes too. Okay. Well, everybody, we got to wrap it up, but we will have you back again, okay? Matt Taylor, Dr. Matt Taylor at the University of Calgary in Alberta. Thank you so much for sharing your knowledge and your expertise and your culinary skills with us today. Thank you so much.
Oh, my pleasure. It was super fun. Thanks for having me.
As always, our co-host, Allen Liu, thank you so much for making this show everything that it is. So appreciated. Thank you.
Yeah, you're welcome. Always glad to be here. Always glad to talk with the guests and answer questions and everything.
Wonderful. And for those of you in the audience, thank you so much for being with us today. If you've liked what you've seen and heard, please support us on Patreon. And as always, thank you for being a part of the LIUniverse.